So, which of these structures would you rather build? Pretty obvious choice, right? This structure takes about, I don't know, 5 minutes to build. And this behemoth takes up about somewhere around half an hour to build. Both of these are the same algorithm. It's a modulation system of 16 parallel modulation signals that I've created in a very specific way that I'll talk about later. So, as you can see, one of these is a whole lot easier to put together than the other one is. So I'm going to talk about two things in this video. I'm going to talk about the main event, which is using polyphonic voices for parallel processing. And then I'm going to talk about this modulation system, what it is, and why I'm using it as an example for showing you how to use this type of signal processing to save time. So you don't have to build something like this. Instead, you can build something like this and cut your time down like tenfold. So what am I talking about when I talk about using polyphonic voices, using voices for parallel processing? Well, before I get too far ahead of myself, I do want to address the fact that this is a topic that is covered in the Reactor 5 documentation in chapter 9.3.4 on page 263, using voices for parallel processing. So I'm not going to go through this, but you should know that this documentation exists on the Reactor product page. They have all of the documentation there on their website. And I definitely recommend reading this because this is a very good tutorial here that will show you how to spread your voices apart using the distributor module. And it's a very creative way of spreading the voices apart. However, they don't do it right. I don't know if I'll explain why they didn't exactly do it right. I have a way of doing that, also using the distributor module. I just don't think that they put the right values into the position input, but that's, maybe we'll get to that later. It's kind of a lofty topic, what we're going to talk about. Now, another thing that I want to address, I would much prefer to do this in an environment like Bitwig's Grid, which is more modern and culturally relevant. I think Reactor is looked at as kind of old and dated, and so yeah, it is what it is. But as far as I know, I don't think that you can process polyphonic voices or stack voices. I don't think that you can do this type of parallel processing using the voice index, because that's exactly what this is. And I'm going to go ahead and I'm going to select my bug mode, which will show me what's going on a line. And let's see, will it do that? Yeah, it'll do that. I'm a little bit new to Mac, okay? So I'm doing this on a Mac. This is my first Mac. Okay, so I can zoom in, show you what's on a line. Okay, so yes, it's a bit of a lofty topic, so I'm going to try to explain this for people who don't understand what I'm doing here. So let's get back to this modulation system. What is this? This is a modulation system that I use to create a series of parallel modulation signals on each voice. There is, as you can see on the front panel, and let's use that handy dandy zoom. Okay. As you can see, there's a modulation system on each voice. Each of these is a voice. Voice 1, 2, 3. There's 16 parallel modulation signals that are being generated. And as you can see, and I think this on the right is a little bit, here, let's just turn the rate up a little bit. Okay, get that going a little bit faster. So if you look at each one of these signals, you'll see that it's kind of like a sine wave. It's kind of smooth, but as you can see, they're not moving at a steady rate. they're not moving at a steady speed. They're kind of slowing down, stopping. They'll slow down. It'll speed up a little bit. Sometimes it'll reverse course. They're kind of random. They have a random behavior, but it's a smooth random behavior that I like. That's kind of similar to a Lorenz attractor, or probably, I think, a better example would be like something called Perlin noise. And the idea is to get a random behavior, but random modulations that are smooth and predictable. The reason that I use this method, and let's just zoom back out, the reason that I use this method is because it's predictable. And when you start smoothing, like there's like a slow random LFO that's stock. It's one of the primary level modules that's built into Reactor, and it's a good module. But the problem is two things: it's jittery and kind of spastic, and it's smoothed. And when you introduce like a slew limiter, I think a slew limiter is kind of like a delay based kind of thing, and because of that, you can tend to overshoot the modulation range that you're aiming for. And the reason that that's a problem is because I use this modulation system to modulate each of the delays in my reverbs, the reverbs that I make in Reactor, which the reason that I'm talking about this is because we're going to get into making some good reverbs in Reactor, and we're going to use this modulation system to make those reverbs, to make the modulation in those reverbs sound good. But I don't just use this modulation system for reverbs. I use this modulation system for my synths too. I use this modulation system to create per voice oscillator drift, and I sample and hold these modulation signals and send them to the filter to create slop, or to decalibrate envelope parameters. It's just a great way to create a series of parallel modulation signals that are smooth, random signals. And I think Perlin noise is really kind of what I was going for. I'm not smart enough and educated enough to know how to actually implement Perlin noise, especially let alone on a per voice basis. But let's get back to using polyphonic voices for parallel processing, now that we know what this modulation system is. So as you can see down below, we've got the same thing, but I have had to do a lot of the same thing over and over again, as I have had to create these sine sync oscillators, and I've had to plug in this random generator to randomize the phases, and I've had to run that into a multiplier. I've just had to do the same thing over and over. I've had to do the same thing 16 times. Okay, so using polyphonic voices for parallel processing isn't necessarily something that you're gonna, it's not necessarily a type of signal processing that you're going to need to use or want to use all of the time. But if you are building something and you're finding yourself having to do the same thing over and over again, then this type of signal processing will absolutely save you time. Okay? So I'm going to leave a link in the description, because this poly display is what you see here. This is what's actually visualizing each of these polyphonic signals. And I actually did not build the display. The display was made for me by a very nice person on the Reaktor Forum. I believe they went by the moniker Big Gnome on the old Reaktor Forum. I'm not sure if they call themselves that anymore, because the Reaktor Forum has kind of gone through a reboot. But I'll leave a link in the description that will link you to this poly display that's on my account on the Reaktor user library. So you can just go ahead and grab this poly display and you can follow along. So let's get into it. So how do we go about saving time, not having to do the same thing over and over again? How do we do this? Okay, so I'll scroll down a little bit. I hid these down below. You're going to be using these modules here, okay? You're going to be using voice info, the to voice module, the from voice module, and the voice shift module. And you're also going to be using the audio voice combiner. You're probably already familiar with the audio voice combiner from having to make polyphonic instruments in Reactor, and at the very end of your polyphonic signal chain, you have to plug everything into these audio voice combiners to convert that polyphonic signal to convert that polyphonic signal to a mono output, because your left and right outputs are mono. Those are mono outputs. So you probably already know what the audio voice combiner is, which is located in the built-in modules in the auxiliary. That's where your audio voice combiner is, and the rest of the voice modules are also in here. Okay, you zoom into that too. As you can see, the most important one is the voice info module, and you can also in here. This is where all of the voicing modules are. The to voice module is also here. The from voice module is also here, and the voice shift module is also here. So audio voice combiner, okay, to voice, from voice, voice shift, and voice info. Okay, it's in the auxiliary part of the built-in modules. Okay, built-in module, auxiliary. That's where they are. Okay. All right. So I'm just going to talk about the first two outputs of the voice info module because it's all I really use. Okay. And as you can see here, I actually haven't needed to use it for this structure, but sometimes I do use it. Now I've got something in my library called polydisplay, and I'm just going to use it just to plug it in to get an output. You don't have to worry about it. We're going to hover over the output of this V output. The V output, as you can see, just gives you those, it's literally the voice index. You're looking at the voice index. I'm going to need a drink of water. This is a lofty topic. Just have some patience. We're going to be here for a minute. Okay. You are looking at the voice index. Okay. And the voice index coming out of this output just outputs voice. On voice 1, you literally have a value of 1. On voice 2, you literally have a value of 2. On voice 3, you have a value of 3, and so on and so forth. No matter how many values you go. Voice 1 will just output 1. Voice 2 will output 2, and so forth and so on. Okay? That's not always what you will have on your voice index, but coming out of this output from this module, that's what you will have on each voice. Just the number of the voice. Okay? And this is super simple. It's just the number of the voices that you have. You have 16 voices. The value of 16 comes out. Okay. These top two, it's actually all I ever use. Okay. I'm either going to, and let me show you something why I would use this. Okay. Let's say that I'm creating a sine wave, and I want to stack on top of the fundamental frequency all of the frequencies of the harmonic series. Hopefully you're aware of what the harmonic series is. They are just multiples of the fundamental frequency. So, well, let's go with something lower. That's awfully high. So let's just go with something a little bit more like 400. Okay, so... and we're just plugging it into the poly display just to see what's on that wire. So as you can see, all right, we have the fundamental frequency coming out being converted to logarithmic pitch. Actually, let's just get rid of this log F. I often do the log F so I can plug it right into an oscillator. But for this example, we don't need this. Okay, so we have 400 hertz coming in, and we have the voice index showing us we have the voice index coming into the multiplier. All right. And so as you can see, when you input the voice index to the to the multiplier module, you multiply that frequency by 2, by 3, by 4, okay? It's just multiples of the fundamental, all right? This is a quick and easy way to get the harmonic series, okay? This is actually, if you're aware of, what is it called? The drone, the old classic drone machine from Reactor. It's not Space Master, it's Space Drone, I think it is. It's basically a giant vocoder. If you wanted to create like a vocoder effect, you would just basically use this. It just creates multiples of the fundamental frequency. Boom, you've got the harmonic series, okay? So that's one example of why you would want to use the voice info to basically do something. It wouldn't really make very much sense to use a bunch of a bunch of multipliers to say, okay, this is 400 hertz times 2, 400 hertz times 3, 400 hertz times 4, and so on and so forth, right? That would be a waste of time. And then you would end up with this massive structure like this that would take hours to build, okay? So by using this module, okay, we don't have to do that. As you can see in this massive structure that we don't have to build because we're using polyphonic voices for parallel processing, you can see that there's a sine wave with an amplitude of 1, but that constant of 1 also goes out to the sync input. And the reason that the 1 is also going out to the sync input is because the sync input is looking for any value that's greater than 0. It kind of works almost like a sample and hold trigger input, which will just look for any value that rises above 0, and it will just be on. It will just accept any value that's coming into it. And that's basically what this sync input of this sine sync module will do. And as you can see up here, we have the same thing. We have that value, that amplitude of 1 going out into that sync input. So it can accept this random series of values between 0 to 1, which I believe will just be phase values from 0 to 180 degrees, I believe. And that is a very important aspect of this modulation system. Is for the phases of all of the sine waves to be randomized, or either spread out or randomized. They can't be the same thing, because if we don't have this happen, we can just kill this wire. You can see that the poly poly structure has all of the sine waves are the same value, and so it's flatlined, okay? This is a really interesting thing here, okay? So when we randomize the values and then turn the structure back on, all of a sudden you have movement. This is actually something I discovered, is that if I created a series of sine waves and I randomized the phases of all of them, and I basically modulated the frequency of the second oscillator after it with the first one, and then modulated the frequency of the third oscillator with the output of the second oscillator, and so forth and so on. I have this daisy chain of what I like to refer to as recurrent frequency modulation, which I just kind of refer to as RFM, which I think is something that's already a term that's already taken, I think, in the world of shortwave radio. But for the sake of remembering what things are, I just call this recurrent frequency modulation, because recurrent modulation is a modulation source that ultimately returns to itself after modulating a series of things. And that's literally what's happening here. Sine wave 1 modulates the frequency of sine wave number 2. Sine wave number 2 modulates the frequency of sine wave number 3, and so on and so forth until we get to the 16th sine wave, which wraps back around and modulates the frequency of the first sine wave. And this would usually result in chaos, but, and here's the trippiest part of this, you will see, and it's easier to show actually up here because it's less chaotic than down there, that all of these sine waves, and you got to remember when you look at this, there's 16 of all of this happening, okay? All of these sine waves have a frequency of 0. 0. Nothing. Wait a minute. How is it possible that I have all of these sine waves creating this movement when all of the sine waves are receiving 0 hertz? Well, that's where these random phases come in. All of these sine waves are modulating, well, all of these sine waves are sending their signal output to the frequency input of these sines of each other's. They're going into here, right? In this big daisy chain, okay? And what that frequency input does, if you know how an oscillator works, is that the frequency input will simply accumulate. It'll basically inputs into a phase accumulator, and it will basically take that signal and it will basically send it into like a ramp generator, and it will accumulate this signal. And that signal will go to the sine function, and that's what tells the sine. That's what creates the sine function. Okay, you need a phase accumulator for that. And so even though we have an input of 0 hertz, the fact that all of these are at random phases causes the phase accumulator to see the signal that's coming in and saying, wait a minute, this, whatever the phase value is, 0.260, 263065, right? It's going to see that it's not 0, right? The phase accumulator is going to see this signal coming in and saying, wait, I'm not supposed to be at a phase value of 0. I'm supposed to be at this 0.26, whatever. And the phase accumulator will tell the sine function to go to that phase value, okay? Which will be just another point in its duty cycle. And when that happens, it tells the next one to do that, and that one tells the next one to do that, and so forth and so on. And because you have all of these random phases on all of these sine waves that are set to 0 hertz, the differences in the phases will basically cause this to happen, which is really trippy. I think that's really cool. Okay, they're all receiving 0 hertz. They're not receiving any direct pinch information, but the differences in the phases cause all of these sine waves to start moving in this beautiful, random way that creates this wonderful series of, well, not really series, it's a parallel process, these 16 parallel signals. But you can do this hundreds of times. Okay, you can have an ensemble that's hundreds of voices large, like Space Drone. It's like 140 partials or whatever. You could have this poly display displaying hundreds of these signals. I've done this. I've actually made an ensemble like that to create these just gorgeous drones, because you can hear these as well. We're not doing anything today that we're going to hear. You're just going to see it all because we're dealing with the modulation system on a scope. But this is that's why I love this modulation system. I use it in everything. I use it in all my reverbs. I use it in every synth that I make, just because it's a great way to control a series of signals that create these just beautiful, predictable, controllable modulation signals that don't give me any unexpected results. Now, let's get to this rate knob. How am I controlling the rate? If I don't have any direct pitch information, if I have 0 hertz, then how is it that I'm controlling the speed? That's pretty trippy. Okay, so let me grab this one. Okay, so ignore this multiplier. That's basically just a power function that's basically controlling an exponential curve, which is something that we can get into in a different video. But the rate is basically, ignore this crossfade function too. That's some extra stuff, okay? It's going out to these multiplier modules. And what is that doing? And I'm not just doing it once, I'm also doing it like 3 more times over here, okay? But it's going out to all of these multiplier modules. So what do these multiplier modules do? And this is going to be easier to show you on the poly structure, okay? But as you can see on this massive, completely unreasonable structure that we don't have to build, these multipliers are attenuating the amount of the signal that is passed on from one sine wave to the next into these frequencies. So we're actually controlling the amount of the signal that is passed on into the frequency inputs. And that is what actually gives you the ability to control the speed of the modulation. The more of the signal output that we pass on to the frequency inputs, the faster it appears to go, or the faster these signals move. Okay? So the amount of frequency modulation basically is what's controlling the rate. Isn't that crazy? Okay, and the depth control is basically just attached to the output. They're just multipliers on the output, okay? And as you can see, this crazy structure that we don't have to build it's got 16 individual outputs. As you can see outside of it, you've got these 16 outputs, right? We don't have to deal with that when we work on the poly level. So let's go back to the poly level. Okay. And so as you can see, now that we know what's going on in this modulation system, as you can see on the poly level, we don't have to really do much. All I had to do was create a sine sync oscillator with a constant going into the amplitude, okay, amplitude of 1, so it's on, and send that constant into the sync input. So it'll receive these random phase values that range between 0 and 1. And that's what happens when you will input a randomized module, which is in the event processing. Let's talk about the randomizer for a second. Okay, so that's where it's at. And it will create a series of bipolar random signals. It's very, very important for you to remember the bipolar part of it, okay? Because this bottom input, which I've also fed that 0.5 into, that's going to be your starting point. I like to think of that as the starting point. You're going to create a series of random signals, but it's going to be bipolar. So we're going to start at 0.5, and then we're going to create a series of random signals. And we have 16 voices. Our ensemble has 16 voices. So obviously, it's going to create 16 random signals the instant that you start the instant that the ensemble opens. It's just going to instantly generate those 16 random values. Okay, but they're not just going to go up to 0.5. They're going to be bipolar, which means that they're going to go down to negative 0.5 as well. And because they're going to go down to negative 0.5, it's very important for us to make sure that this bottom port is receiving 0.5. Okay, so if our starting point is 0.5 and we have 16 random signals ranging from negative to 0.5 to positive 0.5, then we're going to end up with 16 random signals ranging from 0 to 1. Okay, I hope that makes sense. And that's how we're getting these 16 random signals ranging from 0 to 1. That randomizes the phases of all of those sine wave oscillators. And the output of this is a little bit difficult for you to see because I've made it nice and tidy, which sometimes isn't the best way to go. Let's pull out a little bit here. All right, there we go. Which doesn't necessarily make it easier to see. In a way, it makes it a little bit more. Okay, so we've got this. So, okay, the output is being fed into a voice shift module. Let's talk about the voice shift module for a minute. Now, remember what I was showing you with the, where did I put the, there it is, the poly display. Remember when I was showing you the voice index? Okay, 1, 2, 3, 4, 5, that's your voice index, right? The voice shift module will do exactly what the name implies. It will shift the voice index. So if we take the output of this, okay, and as you can see, we have voice 1, 2, 3, 4, 5, 6, blah, blah, blah. Okay, and let's just plug that in there. And as you can see, you just, you get 0, 1, 2, 3. And the reason that it's doing that is because of these next two things that I will show you. Let's just breathe. It's a lot. Okay. Let's take our time. I might receive a phone call. Something might happen. I don't know. Life is chaotic. So the voice index comes in. And then I have the ability to shift the voice index. So I am going to set this to 1, and I'll tell you what that does in a minute. But for the sake of confusion, I haven't shifted my voices at all. So the result is still what's on voice 1, a value of 1. What's on voice 2, a value of 2. 1, 2, 3, 4. Okay. Simple voice index, nothing dramatic has changed. But if I decide to shift the voice index by 1 voice, what happens? What's on voice 1? 16. Okay, so what did it do? It shifted the voice index. Okay? It took that 16 and it wrapped it. It wrapped the voice index. So voice number 16, which is outputting 16, obviously, it wrapped that voice back around. So now what's on voice 1 is 16. Okay? Now I can also go backwards. I could go -1. What happens now? Oh, it wrapped it, but it wrapped it in the other direction. So now what's on voice 1 is 2. And maybe I want to shift it forward. Shift it positively by 4 voices. Now what's on voice 1? 13. What if, this does seem to make a little bit more sense when you do it negatively, just psychologically. Okay, so let's shift it negatively by 4. What's on voice 1? Sometimes it does this weird thing. When I do something, it'll go ... what it used to be, which is annoying. Delete this wire and put it again. I'm still doing it. That's annoying. Anyways, I annoy the ... 5. Okay. So now voice 1 is outputting voice 5. Okay. And it would be nice if those confusing ... and then some other value would show up. That's not what's there. It's 5. Okay. So what does this do? Wrap. Well, this is literally a wrap function. Remember when I told you what this module is doing? It's wrapping the voice back around, either positively or negatively. And in order to actually wrap the voice, you have to have this wrap function turned on, right? So a value of 1 is actually what turns that wrap function on. Okay, so that's what it's doing. It's wrapping. Finally, those ... things are gone. So we're wrapping the voices around when we shift the voice index forward. Well, from a technical point of view, we're shifting it negatively, so it's backwards. It's a little tough to get your head wrapped around, if you know what I'm saying. Okay, so yes, it's wrapping the voices. It's wrapping the voice index, rotating it. It's shifting the voice index. I just want it to make sense, okay? But wrapping the voices is not the only thing that we can do with this voice shift module. We can turn the wrap function off by simply inputting 0 into the wrap input. And that turns the wrap function off. And when the wrap function is off, what does it do? Look what's happening to the last 4 voices. I can't move my mouse down there because then it will move it away from the wire and then you won't be able to see what's on that wire. But as you can see, it's because the wrap function is off, those last 4 voices are outputting 0. That's what happens when, that's not necessarily a bad thing either, because I often use this. I've used this in a width module for one of my FDN reverbs. And by turning that, you can actually use that for like a distributor module. It comes in very handy for actually panning voices apart, hard panning a certain number of voices left or right. That's a different video. Okay, that's a different video. We'll get to that. That'll actually be in the application reference. It's actually part of that tutorial. Okay, but just to further solidify this, if I have +4 going in there, the first 4 voices are now outputting 0. That's what happens when you turn the wrap function off, and it can be very useful. Okay, so we have covered the voice info module, and we have now covered the voice shift module and what that does. And the reason that I just talked about that voice shift module is because I was showing you what happens with the sine sync. Okay, the output of our sines go into this voice shift module. And why did I put, why am I shifting those? The reason, see, I've got the wrap function turned off, and that value of 1, it turns the wrap function on. Did I say it was off? It's on. Okay. The wrap function is on, so it's going to be wrapping, and it's shifting the voice index by 1 voice. And what do we know what happens? Because we already looked at what happens when we do that. We know that the first voice is going to be 16, right? Because we already did that just a minute ago. So we know that the first voice is going to be 16, and we know that the second voice is going to be 1, and the third voice is going to be 2. And that is going to correlate with what we see here happening in this big, huge structure that we don't have to build, is that we know that the signal coming out of this 16th sine wave, coming out of this multiplier, is going into the frequency input of the first sine wave. And that's exactly why you use the voice shift module for this. So we take the outputs of these sine waves, we run them through the voice shift module to wrap the index, to shift the voice index forward by 1 voice. So the first voice that is now a part of the shifted voice index is 16. So we have that happening here. So if you can just mentally just picture everything that we're doing here is happening 16 times. So the 16th sine wave is going into the frequency input of the first sine wave, and the output of the first sine wave is going into the second sine wave. That is a very quick and easy way to be able to modulate, to get that recurrent frequency modulation very quickly and very easily by simply using a voice shift module and putting 1 into each of those inputs. And I sent it into a multiplier module, and I already showed you the multiplier module that passes that signal on to the frequency inputs of the next sine wave, and then the next one after it, and so forth and so on. And then it wraps back around, back into itself. Okay. The amount of that signal that's passed on is what controls the rate. Now, I've used a crossfader with a thing that is basically just to get everything moving. And then this multiplier here is simply the depth. It's just simply what's passed to the output. And what is passed to the output isn't saying anything because it's not plugged into anything on the outside of the macro, but we're going to just plug it in to here, into this poly display, just so we can see that indeed we have these random modulations that we can create, that we can speed up or slow down with that rate knob that's controlling that multiplier. And then this is just a depth knob that's just passing the amount of that signal out and just sending it out of the macro. Okay. So I know that that's a lot to internalize. That's a lot to absorb. But if you can just kind of wrap your head around this type of signal processing, man, you can really save a lot of time when you work on the primary level. But one thing that I haven't shown you is what these to voice and from voice modules do. And we don't really need to use these modules at all to create this modulation system. But in a nutshell, the to voice will basically receive a monophonic signal, and it will take, let's say we have like 8 voices or whatever, or 16 voices or whatever. And let's say that I want to have 12, a value of 12 for whatever reason. That would just be one mono signal, right? It takes that information and then it puts it on a polyphonic wire. So the output will be a polyphonic signal. Where's my poly display here? That's what I have this polyphonic display for. That's what's great about it. I might, on the Reactor user library, I might bundle all of these poly devices that I've made for this type of signal processing, so this will all be useful. But as you can see on voice 7, we have that value of 12. But you can also see that this is a polyphonic wire. It's very important for us to know the difference between a monophonic wire and a polyphonic wire. A monophonic wire just has just one thing on it, just one signal. A polyphonic wire obviously is polyphonic, so it has whatever the amount of voices you have, that's what you see. Voices 1 through 16, and obviously we aren't doing anything with the other voices, so they all say 0. And as you can see, that we have assigned 12 to that voice. Okay, the from voice module, and let's just plug this in. The from voice module basically does the opposite of what the to voice module does. It receives a polyphonic signal. Okay, so let's receive this polyphonic signal with nothing happening on the other voices, but we have 12 on voice 7, right? So let's say that I had this polyphonic signal with other values, or it doesn't necessarily have to be values. They could be audio signals. It's not just a constant value. It could be an audio signal. It could be who knows? I could have this crazy mixer with literally 12 musicians and, outputting 12 audio signals into a giant mixer, right? So maybe Steve is on voice 12, right? Let's say the value of 12 is Steve, and Steve is playing the drums, and he's got his drums mic'd up, and that's the signal that I want to receive on this giant 16 voice mixer. Apparently I have this huge thing going on with 16 people outputting 16 individual mono signals. I guess everybody wants to have a mono signal output for some reason. But anyways, so let's say I'm receiving that polyphonic signal and I want to just receive Steve for some reason. And maybe I want to do something with Steve's drum signal. Then maybe I want to send it through a ring modulator or compress it or EQ it or whatever, right? And so coming from voice 7. Wait. It comes in. Voice number. There you go. I don't know why it was saying nothing. So there you go. There's 12. There's Steve, right? There's Steve's drum. And I just basically just cherry picked that part of the signal. So this is kind of a sloppy way of me just showing you that the two voice module will just take one piece of information, one little signal, basically a mono signal, and it'll put it on a polyphonic wire. And the from voice module will basically look at that polyphonic wire, and I can tell it to just cherry pick information on that one voice, on voice 7. So it does the opposite of what the two voice is doing, and it just gives me that one signal. Hope that makes sense. Whew. Let's breathe again and have a drink of water, because it's a lot to go over. But it's a very useful type of signal processing that will save you time, will absolutely save you a lot of time, and you can do a lot with this. There's a lot of applications for using polyphonic voices for parallel processing. And yes, you should absolutely read that part of the application reference from the Reaktor 5 documentation on the NI website. Absolutely go in and read it, learn from it, learn how this type of signal processing works, because it's extremely useful. And this modulation system is just one type of thing that you could make using this type of signal processing. I use this modulation system, like I said, for my reverbs. I also use it for synths to create oscillator drift on a per voice basis. So you can use it for effects. You can use it for instruments. You can absolutely go bananas with this way of processing. If you can kind of just get over the mental, the psychological thing of not actually seeing what you're doing on each voice, but you're still doing it, right? And like I said, this type of signal processing isn't going to be useful for every single thing that you try to do, but I think if you're building something and you find yourself doing the same kind of thing over and over and over again, and you have this large redundant structure, then using polyphonic voices for parallel processing is absolutely something that can be useful for you and will save you loads of time. Blah, blah, blah. It's a lot to digest, but it's useful and it's cool. And I really wish that we could do it in the grid. And I'm pretty sure that we can't. I really want to. I want to do this in the grid, but I don't think we can do it yet. Yeah, if you want to use stack voices, if you want to have some stack voice modules that basically do the same thing that these modules do, that would be super cool. But yeah, hope you found this useful. I will see you in the next video, hopefully soon, that tackles reverb. Talking about all pass stuff. Talking later on, I think down the road, we'll talk about FDNs and stuff like that. But yes, super important type of signal processing for doing a lot of stuff. That's very cool, and we'll get to it. So, sorry for rambling.